Okay, so now let's do a really speedy test trial over the topic fields. And now let's first start with the gravitational field strength. So, ready? Go. Okay, so for number 7 here, satellite X orbit a planet. This one the same. So this one about orbiting about the planets. So that should have to do with the gravitational field strength, or also like the gravitational acceleration. It asks for the ratio between the centripetal acceleration between x and y. So that should be A. We're thinking of something to do with the r, and they actually on different r here. So the r here, or like the A here, so that should be the G here. They have the same mass, so A will be equals to F over M. So basically this is the A, this is the G, so the G is proportional to the R squared. So if we have the radius as twice, then the G should be decreased, drop by 4 times, so that should be D. Next, number 8, gravitational force between two point masses, and the acceleration is R. So we have this one. This is not a curve, so that's not the one. If it's because this one is the inverse square law. So we have this one actually proportional to this terms here itself. So if this one is the variable, then this is a straight line, so that's D. 9. Planet X has a gravitational field strength of this one, the Y the same density but 3 times the radius. So if it's like 3 times the radius, then it should be like 3 cube of the volume, right? And that's why the mass is would be like 3 cube, like 27 times of the mass here. So it means that the gravitational field strength here should be increased by 27 times, but it also have a greater distance here and at the surface, so then it will be dropped by 3 squared, so 9 times. So multiply by 27 and decrease by 9, then it should be like just increase by 3. So 3 times of this one, it should be 18 times 3 to be 54. Number 10, definitions of gravitational field strength at a point. The sum of the field rate by the masses around the point. It could be, but this is not really the definition, right? So let's check the other one. Gravitational force, yes. Per unit mass, yes. It's by a small point mass, yes, at a point. This is the correct one. C, this one, where this one is the mass minute. Not really, because what if it is just like many planets, right? Not just one, right? And it's maybe just, so this is not the general one. The resultant force is not a force. It's a force per unit mass, so that should be B. Okay. Number 11, gravitational field strength surface planet R G. Now we have another satellite moving in a circular above the surface, another R. So what is the magnitude of the acceleration, or basically the G here? So again, G is also proportional to like inverse square law of the radius. So now if it's here R, now it is like twice. So twice the radius, so it should be dropped by 4 times square. Okay, 2 square 4. So that should be B. 12. A satellite is orbiting Earth in a circular path at a constant speed. This one. 3 statements about the resultant force on the satellite are. This one is 1. So let's see. Equals to this one, gravitational force. About the resultant force? Yes, here, because what? We have the constant speed and circular. So it means that there's only a centripetal. It is only a centripetal acceleration. That should be the G itself, the gravitational acceleration. So this is yes. The mass times with acceleration, yes, that's the ma. That's the Newton's second law. Equal to the centripetal force on the satellite. Yes, so 3 are correct, so that's D. 12. 3 statement about Newton's law of gravitation. It does not explain why gravity exists. It just study the magnitude of the gravitational itself. It can be used to predict the motion of satellite, yes, because from this we can find the acceleration a and then so on. It's used to derive the expression of gravitational potential energy mgh, yes. So this is incorrect, only 1 and 3, so only 1 and 3B. Number 14, the center of the earth and the moon, distance big D, and then we have another point X here, cancel out, the distance is D here, the mass is this one. Okay, so what is correct at X? Because this one cancel out, so the F from the moon should be equals to the FG from the earth, between the earth equals to between the one from the moon. So we have G on both sides cancel out, the same mx and then the same mx also cancel out. So what left here is just the ratio between the mass of the E and the distance from the earth to the X, and this is like the mass of the moon and the distance from here to here, so that should be equals to the big D minus the little d. So this is the one. That's C. 15, the diagram show two equal and opposite charge are fixed in place. Okay, opposite. Okay, which point the net electric field directed to the right, so first here, this is a negative one, so on the electric field towards it, this one is positive, so everything is like outward. So let's check each point. First, for the Z here, we can see this one really near the plus, so this is a big E from the plus, and now this one should be a little less because this is further away from here. So if this one is like greater than this one, then in the end it should turn to the point to the right, so we got the Z. For the Y here, they will just like add up of like two vectors to the left, so no Y. Now let's check for the X. The X here, it will have it pretty near to the negative here, so it's a big one here, and further away from the positive here, so that's just a little here, so more to the right as well, so that should be X and Z only. Number 16, charge, okay, distance 3x apart. Okay, so this is actually 2x. The point on the line showing the charge at a distance x. Okay, got it. Oh, this just basically describes this diagram. Magnitude produced at a charge along is E. So if it's just this one is E and the distance is like x plus here, what is the total at P? First here, this is positive, so at P it will generate a E plus to the right. This is also negative, so it's also towards it. It should be also to the right as well. Let's check about the magnitude. So the one that created by the minus 2q here is like twice the magnitude of q, but like drop by 4 times because the distance also twice, so that like 2 square. So that's why in the end it's just like a half of the electric field caused by this one, so that should be like 1 plus half of it, so that should be 1/2, so that should be 3/2 to the right, so that's a C. Number 17, two charges are placed shown. What is the magnitude of the electric field in the descending order at these 3 points? We have two charges here, the plus one and the minus one here. So let's see. So for the positive here, it should be like on everything like out of it, and for this one is on way like towards it. So for the X is also like toward, the Y towards, the Z towards. So for the Z, first let's check this one this way, from this one also this way. So for the Z, everything just add up, so Z should be the biggest one, the greatest one. Now let's check with the Y and the X here. The Y nearer to this one, and this part is like let's say this is just a 1 unit, so this is like outward for 1 unit here, and then for this one it's just like 1 2 3 4 5. See, 1 2 3 4 5, so 5 times the distance should be like 1/25 the magnitude, so that should be like this way, this much, and then this way is just a 1 over, so it's just the magnitude is just the difference between these two, so just 1 minus 1/25, and then we got this 1/24/25, this one. For the Y, for the X, that should be twice of this one, so this is like 1/4 compared to the unit, the maximum one, and this one is 1, 2, 3, 4, 5, 6. So that should be 1 over 36. So basically they just like two opposite things. So we just need to find the difference. That doesn't care if we do this minus what, but this one, if we got 2 over 9, so we're comparing, then we see y should be greater than x. We can just use the calculator. 24 divided by 25 is like around 0.96, and then 2 divided by 9 is like around 0.22. So the y basically greater than the x. Yeah, so that's zyx. So this is the one, zyx. Number 18. A negatively charged particle in a uniform gravitational field strength in position midway between two charged conducting plates. Okay, so we got a negative here, the positive here, so the electric field should be here. So it's undergo two forces, the Fe in the opposite direction to the E field upward, and the negative and the downward gravitational force. The difference here is adjusted, okay, until at rest, so it means that these two balance out. What changes that cause one downward? So it only downward if we got the Fe decrease. So in order for Fe decrease, Fe equals to QE, we either have Q decrease or E decrease. So now we can see that if we did with the charge, yes, then Fe will decrease because this one decreases itself. Decreasing the separation of the plate, not really, because E inversely proportional to the distance. So if distance is decreasing, then E will be increasing. So this one will be increasing instead, so not this one. Increasing the length of the plate. That does not affect in this case. Increasing the potential difference of the plate. If we increase in this one, the E is also increasing, and this one will be increasing, so that's not the case. So we want here, that should be A.